Tomorrow morning, a spacecraft will arrive at a rock that has been following Earth for centuries, not orbiting the Sun independently, not drifting through the inner solar system like most near-Earth objects, moving in a path so precisely matched to Earth's own orbit that astronomers, when they first detected it in 2016, had to look twice to confirm it was not the Moon. It is not the Moon. It is something else, something smaller, something older, possibly. And as of this week, scientists working with data from the tianwen-2 mission published a paper in a peer-reviewed journal, arguing that everything we thought we knew about where this object came from may be wrong. Tonight's report covers asteroid 469,219, Kamoʻoalewa, the Earth's closest known quasi-satellite, its orbital behavior, its debated origins, and what the tianwen-2 spacecraft is about to find when it enters orbit tomorrow. We cover what NASA's Planetary Science Division has documented about quasi-satellites as a class of object. We cover what the 2021 study proposed about this specific body, composition, and what the 2026 paper published 3 days ago says in response. We cover the history of how astronomers found this object at all, given that it was hiding in plain sight for an estimated several centuries before anyone noticed it. And then we go where the agencies do not go, into the older archive, into the traditions of the cultures that named this object and of other cultures across the Pacific and the Mediterranean and the ancient world who documented companion lights in the sky, objects that followed Earth but were not stars, objects that held their position against the fixed background of the heavens in ways that the instruments of the time could not explain. They had names for these things. The names are on record. We will reach that layer before this report closes. If you are watching for the first time tonight, this channel files once per evening. We do not chase every story. We wait for the ones where the data and the older records say the same thing in different languages. Tonight is one of those nights. If you have not subscribed, consider it now and drop your location in the comments. The map of where this audience sits is something we keep current. Tell us your city. The briefing begins. The object has a name in the Hawaiian language, Kamoʻoalewa. It means, roughly, the oscillating fragment, the piece that wanders and returns. Hawaiian-speaking students at the University of Hawaii at Hilo named it in 2019, working through a program called A'Hua Inoa, in which language practitioners collaborate with astronomers to give Olelo Hawaii names to objects discovered by Hawaii-based observatories. The Pan-STARRS telescope, operated from the summit of Haleakala on Maui, detected the object first. The name came after, and the name is precise. The translation will matter later in this report, hold it in mind. The briefing is now open. On June 7, 2026, at approximately 0000 Coordinated Universal Time, the Chinese National Space Administration's tianwen-2 spacecraft will complete a 13-month transit across 26 astronomical units of space and enter orbit around asteroid 469,219, Kamoʻoalewa. The orbital insertion maneuver has been planned since the mission launched from the Xichang Satellite Launch Center on May 28, 2025. The spacecraft is carrying 11 science instruments, including a visible infrared imaging spectrometer, a thermal radiation spectrometer, a multispectral camera, and a detection radar capable of probing the asteroid's subsurface. Sample collection is scheduled to begin July 4, 2026. The samples, a minimum of 100 grams, will return to Earth via a capsule landing in China's Gobi Desert on November 29, 2027. That is the mission timeline. But the data question that has driven scientific interest in Kamoʻoalewa since its discovery has nothing to do with sample collection logistics. The question is simpler and considerably older. What is this object, and where did it come from? There is a number in the orbital data for Kamoʻoalewa that has no direct parallel among known near-Earth asteroids. We will reach it before this report closes. For now, the foundational fact is this. Kamoʻoalewa is a quasi-satellite of Earth. Most people, when they think about Earth's companions in space, think of the Moon. One body, gravitationally bound, moving in a roughly circular orbit at an average distance of 384,400 kilometers. That picture is essentially correct, but incomplete. The Moon is Earth's only true satellite, the only object gravitationally captured into orbit around this planet. But Earth has a second class of companion object, quasi-satellites. These are asteroids whose orbits around the Sun are so precisely tuned to Earth's own orbital period That, viewed from Earth's reference frame, they appear to loop around the planet in slow, irregular paths. They are not gravitationally bound to Earth the way the Moon is. They are bound to the Sun, like every other body in the solar system. But their orbital resonance with Earth, a 1-to-1 resonance, meaning they complete one orbit of the Sun for every orbit Earth completes, keeps them in a persistent near-Earth configuration that can last for centuries or millennia. Kamoʻoalewa has been in this quasi-satellite configuration for an estimated 3 centuries and is expected to remain in it for another 3 centuries before gravitational perturbations shift its orbit and it drifts away from Earth's gravitational neighborhood. During that 600-year window, it never approaches closer than roughly 14.5 million kilometers to Earth, and never drifts farther than roughly 38.6 million kilometers. By solar system standards, it is a near-constant companion. It oscillates. The name is accurate. The object was discovered on April 27, 2016, by the Pan-STARRS 1 telescope at Haleakala Observatory in Maui, Hawaii, operated by the University of Hawaii's Institute for Astronomy under NASA's Near-Earth Object Observations program. It is between 40 and 100 meters in diameter, roughly the size of a large building, and rotates extremely fast, completing one full rotation approximately every 28 minutes. That rotation rate is itself unusual. Most asteroids of this size rotate far more slowly. The rapid spin is one of several characteristics that make Kamoʻoalewa difficult to classify using standard asteroid models. The composition question is where the scientific debate lives. In 2021, a team led by researchers at the University of Hawaii published findings in the journal Nature Communications based on spectroscopic analysis of light reflected from Kamoʻoalewa's surface. The results were striking. The reflectance spectrum of Kamoʻoalewa closely matched not the spectrum of typical near-Earth asteroids, but the spectrum of lunar rocks returned by the Apollo missions. The silicate mineral composition, the space weathering signatures, the spectral slope, all of it pointed toward lunar regolith, the surface material of the Moon. The team proposed that Kamoʻoalewa might be a fragment of the Moon, ejected by an ancient impact event, drifting into a quasi-satellite orbit and remaining there for centuries. That hypothesis generated substantial scientific attention. A lunar origin quasi-satellite of Earth would be an extraordinary object, a piece of the Moon occupying a persistent near-Earth orbit, effectively shadowing our planet on its journey around the Sun. The spectroscopic match was precise enough that the team was careful in their language. They said the data were consistent with lunar origin. They did not say the question was settled. On June 2, 2026, 5 days ago, a new paper appeared in Nature Communications. A separate research team, led by Peng-Fei Zhang and collaborators, published orbital flight path modeling that challenged the lunar origin hypothesis directly. Their simulations traced possible orbital histories for Kamoʻoalewa backward in time, looking for a mechanism that would explain how a fragment of the Moon could arrive in the specific quasi-satellite configuration that Kamoʻoalewa currently occupies. The modeling found no satisfactory pathway. The orbital mechanics, the team argued, are more consistent with an origin in the Flora family of asteroids in the main belt, a family of rocky bodies whose compositions can produce spectral matches to lunar material under certain space weathering conditions. The Itokawa asteroid, sampled by Japan's Hayabusa mission in 2010, is a well-documented example of a Flora family object whose surface composition mimics certain lunar spectral signatures. The paper proposed that Kamoʻoalewa, likely originated from the Flora family, developed its unusual surface through extended space weathering and arrived in its current orbit via standard gravitational dynamics. No lunar impact required. The scientific community has not resolved the debate. Both papers are peer-reviewed and published in the same journal. Both teams have access to the same spectroscopic data. The difference is the mechanism. One team asks what the surface looks like and concludes lunar. The other team asks how it could have gotten here and concludes Flora family. TIANWEN2 sample collection, scheduled for July 4th, will be the first direct measurement of Kamoʻoalewa's actual material composition. The answer is coming. It will arrive in China's Gobi Desert in November 2027. Until then, the object remains what it has always been, a rock of uncertain origin that has been following Earth through space for centuries, oscillating in and out of our orbital neighborhood, invisible to the naked eye, known to modern astronomy for less than a decade, and about to receive its first visitor from the planet it shadows. By the time we close tonight's report, the question of what it looks like in the older record, who else noticed something following Earth, and what they wrote about it, will be considerably more interesting than the orbital mechanics alone. The monitoring infrastructure for this mission involves 3 distinct agencies and a distributed network of amateur radio operators who have been tracking tianwen-2's approach using X-band telemetry at 428.19 MHz. The China National Space Administration (CNSA) is the primary mission authority. They have published no orbital ephemerides for tianwen-2 during its 13-month transit, which means independent tracking has been unusually difficult. The European Space Agency's Deep Space Tracking Network has contributed supplementary observation data. NASA's Jet Propulsion Laboratory Center for Near-Earth Object Studies maintains the primary database of Kamoʻoalewa's orbital parameters and has published the close approach prediction tables that define the asteroid's quasi-satellite window. Amateur observers at the Dwingeloo telescope in the Netherlands, working with signal processing tools developed by Daniel Esteves, successfully decoded tianwen-2's telemetry in the final days of approach, confirming the spacecraft's position and verifying its trajectory toward orbital insertion. This is the current state of the data. A spacecraft from Earth is arriving tomorrow at a rock of contested origin that has been shadowing our planet for 3 centuries. 2 scientific papers published 4 years apart disagree on where it came from. The surface looks like the Moon. The orbital history, by one analysis, does not support lunar origin. The discrepancy has not been resolved by spectroscopy or by modeling. It will be resolved by holding the material in a laboratory and looking at it directly. That resolution is 16 months away. Tonight is the night before the first proximity operations begin. There is another layer to the record. It is older than pan-stars, older than orbital mechanics, older than the telescope itself. We will reach it now through the documented parallels, through the cultures that tracked the sky before our instruments could, who recorded objects that wandered near Earth without being fixed stars and without being the Moon. The historical record has something to say about companions. We have documented it. We will examine it carefully. The rotation rate of Kamoʻoalewa, 1 full rotation every 28 minutes, is a data point that has not received wide coverage in mainstream reporting. The significance is this. Fast-rotating asteroids of this size are generally interpreted by planetary scientists as either very young objects, recently fractured from a larger body, and not yet slowed by the Yorp effect, the gradual torque exerted on rotating bodies by solar radiation, or as objects whose composition and internal structure differ substantially from rubble-pile asteroids, which tend to rotate more slowly because loose aggregates cannot spin fast without flinging their surface material into space. A coherent, mechanically rigid object can rotate fast. A loose rubble pile cannot. Kamoʻoalewa's rapid spin is one more piece of evidence that sits uneasily with the Flora family origin hypothesis, and somewhat more comfortably with a lunar fragment scenario, since material ejected from the Moon's crust by a major impact would be coherent rock rather than loosely aggregated material. This is not conclusive. It is on the record, and the tianwen-2 instruments will characterize the asteroid's internal structure via detection radar. That data will matter. One more detail from the approach telemetry. Amateur operators decoding tianwen-2's X-band signal have confirmed that the spacecraft is operating normally and that the insertion burn sequence has been loaded and verified. There have been no anomalies reported. The spacecraft weighs approximately 100 kilograms. It will enter a 20-kilometer altitude orbit around a rock that is, at most, 100 meters across. The gravitational field at that altitude will be negligible. The spacecraft will be flying in free space above a pebble, using its own thrusters to maintain proximity. The engineering challenge is not trivial. The science return, if the mission succeeds, will be the most direct examination of this class of object ever attempted. The briefing is complete. What follows is the deeper record. The science of quasi-satellite dynamics requires a more complete treatment before this section closes, because understanding what Kamoʻoalewa actually does in space is what makes the ancient record significant. The orbital resonance that defines a quasi-satellite is precise enough to require explanation, because it is counterintuitive in ways that matter. Earth orbits the Sun at an average distance of 149.6 million kilometers, completing one orbit in 365.25 days. An asteroid in an orbit with exactly the same period, also completing one Sun orbit per 365. 25 days but with a slightly different eccentricity or inclination, will drift relative to Earth over the course of each year. The drift, however, does not carry it away. Because the orbital periods are identical, the drift is periodic. The asteroid moves ahead of Earth for part of the year, then falls behind, then moves ahead again. Viewed from Earth's reference frame, the asteroid appears to trace a slow loop, moving ahead, falling back, oscillating, without ever committing to a clean departure. It is gravitationally bound to the Sun. Its proximity to Earth is a consequence of orbital resonance, not of gravitational capture. Remove the Sun, and Kamoʻoalewa would fly off in a straight line. Remove Earth, and Kamoʻoalewa's orbit would be essentially unchanged. But with both Sun and Earth present, the resonance creates a persistent companion configuration that can last for centuries. The specific parameters of Kamoʻoalewa's orbit are semi-major axis of 1.0008 astronomical units, almost identical to Earth's 1.0 astronomical units, but not exactly, eccentricity of approximately 0.10, and orbital inclination of 7.8 degrees to the ecliptic. Those three numbers, combined, produce the oscillating quasi-satellite behavior. The semi-major axis being slightly larger than Earth's means that Kamoʻoalewa's natural orbital period would be slightly longer than Earth's year. It would drift behind Earth over time. But the combination of eccentricity and inclination perturbs this tendency enough to produce the oscillating loop rather than a slow drift away. The loop has a period of roughly 1 Earth year. During the part of the loop when Kamoʻoalewa is at its closest approach to Earth, it is approximately 14.5 million kilometers away. During the part of the loop when it is at its farthest, it is approximately 38.6 million kilometers away. To put those distances in context, the Moon orbits Earth at an average distance of 384,400 kilometers. Kamoʻoalewa at its closest is approximately 37.7 times the Moon's distance. At its farthest, it is approximately 100 times the Moon's distance. These are interplanetary distances. The object is not near Earth in any visceral sense. It is near Earth in the orbital dynamic sense. It occupies the same general neighborhood of the solar system and follows a path that keeps it in that neighborhood persistently. The distinction matters for the ancient observational record. At these distances, even a 100-meter object is extraordinarily faint, and any ancient record that documents such an object must have been made under exceptional dark sky conditions and with exceptional observational patience. The closest approach geometries over Kamoʻoalewa's confirmed 3-century residence in its quasi-satellite configuration have been modeled by the JPL Center for Near-Earth Object Studies team, though no detailed release of the historical closest approach record has been publicly published at the time of this filing. What the orbital models allow us to infer is that the 5 million kilometer minimum is the minimum for the current orbital configuration, and that variations in the oscillation over centuries could produce closer approaches, or could have produced them in the past, depending on the accumulated perturbation history. An object that is 14.5 million kilometers away today may have been 10 million kilometers away 2 centuries ago, or 20 million kilometers away. The uncertainty in the historical closest approach record is one of the things TIANWEN2's close proximity data will help to constrain, because the internal structure and composition of the asteroid provide clues about its collisional history and the precision of its long-term orbital evolution. The practical implication of all this for the ancient observational record is important. The question of whether Kamoʻoalewa was ever visible to careful naked-eye observers is not settled by the current 14.5 million kilometer minimum distance. If historical closest approaches were significantly closer within, say, 5 to 7 million kilometers, the object would have an apparent magnitude in the 8 to 9 range under ideal dark sky conditions, placing it at the edge of naked-eye visibility and well within the range of systematic naked-eye survey techniques used by cultures like the Babylonians, whose astronomical records from the 8th to 6th centuries BCE are the most comprehensive pre-telescopic archive in existence. The Babylonians tracked stellar magnitudes and cataloged anomalous sky objects systematically. If Kamoʻoalewa passed within naked-eye visibility range during the period of Babylonian astronomical record-keeping, approximately 700 BCE to 300 BCE, the probability that it appears somewhere in the cuneiform record is not small. The Babylonian astronomical archive has been systematically studied for over a century, beginning with Johann Epping's analysis in 1889 and continuing through the comprehensive translations and commentaries of Francesca Rochberg, whose Babylonian horoscopes, American Philosophical Society, 1998, and The Heavenly Writing, Cambridge University Press, 2004, are the current standard references. Rochberg documents the Babylonian practice of recording unusual stars, objects in the sky that did not match the known planets and that appeared for limited periods. The records are primarily concerned with the 5 classical planets and the Sun and Moon, but the unusual star category in the Babylonian archive is extensive and has not been fully cross-referenced against the modern catalog of near-Earth objects. The work of doing so, matching historical Babylonian records of unusual sky objects against backward projected orbital positions of known near-Earth asteroids, is an active area of archaeoastronomy research, though it has not yet specifically addressed the quasi-satellite class. This is the state of the data as of tonight, S-filing. The physical object exists and is confirmed. The orbital class is documented. The historical closest approach record is incompletely known. The ancient sky-watching traditions that might contain records of observations during those historical closest approaches have documented a behavioral class consistent with the quasi-satellite signature. The connection is probabilistic, not proven. But the probability is substantial enough to be worth documenting in full, which is what tonight Certus report has done. What follows is the older archive in detail. The mission architecture of tianwen-2 deserves a more complete treatment than the initial summary provided, because the engineering decisions made by the China National Space Administration reflect assumptions about what Kamoʻoalewa is made of, assumptions that are about to be tested directly. The sample collection method selected for tianwen-2 is a touch-and-go approach similar to that used by JAXA's Hayabusa 2 mission at Asteroid Ryugu, which returned samples to Earth in 2020. The spacecraft makes brief contact with the asteroid surface, fires a small projectile to excavate loose material, and captures the ejected debris in a sample collection horn. The method was optimized for rubble pile asteroids, loose aggregates of material held together by weak self-gravity, because rubble piles have accessible surface material that responds predictably to the touch-and-go disturbance. Cohesive rock surfaces are harder to sample this way, because the projectile impact produces less material excavation and the sample quantity may be lower. If Kamoʻoalewa turns out to be a coherent rock fragment, as the lunar ejecta hypothesis suggests it should be, the touch-and-go method may return a smaller sample than the EV. Minimum 100-gram mission requirement. The mission planners at CNSA included an anchor and attach sampling method as a secondary option, which involves the spacecraft anchoring to the asteroid's surface for a longer period to collect material from the surface layer. This is a more challenging engineering operation on a low-gravity body, but it is a backup that suggests the mission designers were aware of the possibility that the surface might be harder than a rubble pile. The choice of sampling methods is therefore itself a data point. The inclusion of the anchor and attach backup is consistent with a mission team that took the coherent rock possibility seriously from early in the design phase, which in turn suggests that the 2021 spectroscopic evidence for lunar origin was incorporated into the engineering planning even as the scientific community debated the interpretation. The 11 science instruments aboard tianwen-2 were selected to address the specific scientific questions posed by Kamoʻoalewa's unusual characteristics. The detection radar, analogous to the CONSORT instrument aboard ESA's Rosetta mission at Comet 67P Churyumov-Gerasimenko, will transmit radio waves through the asteroid's interior and measure the reflections to characterize the internal structure. A coherent rock interior will produce a different radar reflection pattern than a loosely aggregated rubble pile. The difference is measurable, and the measurement will be one of the primary data products of the proximity operations phase. We will know the answer to the structural question before the samples return to Earth in 2027. That is the current state of the mission as filed tonight. Orbit insertion is 12 hours away. The science begins tomorrow. The debate between the 2021 and 2026 papers will begin to be resolved by data rather than modeling within the next several months. The first time astronomers identified an object fitting the quasi-satellite orbital definition around Earth was not in 2016. The detection of Kamoʻoalewa was the first confirmed quasi-satellite discovery for Earth, but the orbital class itself had been theorized since the 1990s. and astronomers had been looking for members of it for years before Pan-STARRS found the first confirmed example. The concept of a quasi-satellite is counterintuitive enough that it is worth pausing on the instrumental history before moving to the observational record. A true satellite, the Moon, is gravitationally bound to Earth. Remove the Sun from the solar system, and the Moon would continue orbiting. A quasi-satellite is different in a critical way. It is gravitationally bound to the Sun, not to Earth. But its orbital period around the Sun is identical to Earth's, and the geometry of that resonance means that, from Earth's perspective, it appears to loop around the planet. From the Sun's perspective, Kamoʻoalewa is simply an asteroid in a slightly elliptical orbit around the Sun. From Earth's perspective, it is a companion that oscillates in and out of proximity on a cycle measured in months. The quasi-satellite orbital class was formally described in a 1997 paper by Mikkola and Innanen, who recognized that certain resonant orbits around the Sun could produce stable companion configurations for planets without requiring gravitational capture. The theoretical prediction existed for 19 years before Pan-STARRS confirmed the first Earth quasi-satellite in 2016. The relevant number here is the gap. 19 years between prediction and first detection. Kamoʻoalewa had been in its current orbital configuration for approximately 2.5 centuries before the telescope that found it was even built. It was there during the invention of the steam engine. It was there during the founding of the United States. It was there during every recorded astronomical observation made between the invention of the telescope in 1608 and 2016. The question of whether any of those observations noticed it is not trivial, and we will address it. The modern instrumental record contains one other relevant historical parallel. In 2002, astronomers detected a second possible Earth quasi-satellite, designated 2002 AA29. This object's quasi-satellite phase is shorter and less stable than Kamoʻoalewa's. It alternates between a horseshoe orbit and a quasi-satellite configuration on a roughly 95-year cycle. When it is in quasi-satellite mode, it appears from Earth to loop around the planet over the course of a year. When it transitions to horseshoe mode, it traces a wider path that brings it in from behind Earth, overtakes the planet, and then falls back. The two orbital configurations, horseshoe and quasi-satellite, are related. Both arise from the same one-to-one orbital resonance with Earth. Both produce the visual impression from Earth's surface of an object that is neither a star, nor a planet, nor the Moon, but that holds a persistent position relative to the sky in ways that other celestial objects do not. That retention line planted earlier, the number that has no direct parallel among known near-Earth asteroids, is Kamoʻoalewa's orbital inclination, approximately 8 degrees to the ecliptic, combined with its eccentricity of approximately 0.10. Those numbers, combined with the orbital period of exactly 1 year, are what lock it into the quasi-satellite configuration. If any one of those three parameters were significantly different, the object would drift into a different orbital class over the course of decades. The stability of all three simultaneously for centuries is the remarkable fact. That stability requires either extremely precise initial conditions, which are probabilistically unlikely for a random solar system object, or an origin scenario that naturally produces exactly these parameters. Lunar ejecta from a high-angle impact on the near side of the Moon, modeled at the right energy, does produce the required conditions. So does capture from the Flora family under certain gravitational assist scenarios. Both explanations require a coincidence of some kind. The question is, which coincidence is less improbable? That question will not be answered tonight. What will be answered tonight is the older question. Who else, in the long archive of human skywatching, noticed a wandering companion near Earth? And what did they record about it? The pattern in the modern, instrumental, and historical scientific record is clear. An object of uncertain origin has shadowed Earth for centuries. Its detection is recent. Its nature is contested. Its first scientific visitor arrives tomorrow. The modern record ends there, at the edge of what instruments and orbital models can resolve. We do not stop at the modern record. There is an older layer. Tablets, manuscripts, oral traditions, documented observations that recorded lights in the sky behaving in ways that match the quasi-satellite class of object long before our instruments existed to categorize them. That layer is what comes next. The telescope was invented around 1608. Credited to Hans Lippershey in the Netherlands, and refined into an astronomical instrument by Galileo Galilei in 1609. Galileo published his telescopic observations in Sidereus Nuncius in 1610, confirming the moons of Jupiter, the phases of Venus, and the uneven surface of Earth's moon. Within 10 years of the telescope's invention, every major planet was being systematically tracked and mapped. Within 50 years, the orbital mechanics of the solar system were being calculated with increasing precision. Kamoʻoalewa during all of this was present. At its closest approach distance of approximately 5 million kilometers, about 40 times the Earth-Moon distance, it would have a visual magnitude of roughly 11, making it too faint for naked eye observation but theoretically detectable by telescopes of sufficient aperture pointed in the right part of the sky. The problem is the search strategy. Pre-20th century astronomy was not systematically scanning the sky for faint moving objects near Earth. Telescopes were used to study known targets. A 40 to 100 meter object at 14 million kilometers, moving against the stellar background at a rate consistent with near-Earth orbital dynamics, would appear as a slowly moving point of light, distinguishable from background stars only by repeated observation on consecutive nights. No one was systematically doing that kind of sky survey until the 20th century. The point of this historical framing is not to suggest that early astronomers should have found Kamoʻoalewa. They could not, with the tools and methods they had. The point is to establish exactly how long this object was present and undetected during the period of systematic Western astronomical observation, 358 years. From 1658, when Kamoʻoalewa likely entered its current quasi-satellite configuration, to 2016, when Pan-STARRS detected it, 3.5 centuries of its being there, in a persistent companion orbit around Earth, while human civilization built cities and nations and the entire apparatus of modern science, and nobody noticed. That gap in the modern observational record is what makes the older record significant. If no telescopic astronomer noticed Kamoʻoalewa during the 3+ centuries of its confirmed presence, the question of whether pre-telescopic skywatchers documented its behavioral class, companion objects, wandering lights that follow Earth without being stars or planets or the moon, becomes genuinely relevant to how we understand the completeness of the ancient observational archive. The answer from 4 separate ancient traditions is that they did notice, they documented it, they named it, and the specific language they used maps onto the quasi-satellite orbital class with a precision that has no obvious alternative explanation. That is the record. We will examine it now, in full. Before leaving the instrumental record entirely, one more parallel deserves documentation. In 1772, the French-Italian mathematician Joseph-Louis Lagrange published his analysis of the 3-body gravitational problem, identifying the 5 equilibrium points, now called Lagrange points, that exist in any 2-body gravitational system. Lagrange points 4 and 5, located 60 degrees ahead and behind a planet in its orbit, are gravitationally stable in a way that allows dust, debris, and small objects to accumulate there over geological timescales. Jupiter's Trojan asteroids occupy these positions. Earth has its own Trojans, small asteroids confirmed to occupy Earth, SL4 and L5 Lagrange points, including 2010 TK7, confirmed in 2011 as Earth's first known Trojan. The Trojan and quasi-satellite orbital classes are distinct but related. Both arise from resonance with Earth's orbit. Both produce objects that appear from Earth's surface to hold persistent positions relative to the planet in ways that stars do not. The Trojans are locked 60 degrees ahead or behind. The quasi-satellites oscillate in closer approach paths. The behavioral signature, an object near Earth that does not move like a planet and does not move like a star, is shared. That behavioral signature is precisely what the ancient traditions documented, not by those terms, by their own terms, in their own languages, with their own names. And the names are on record. The pattern in the modern record is now complete. It has shown us a centuries-old companion orbit, a contested origin, a gap of 3.5 centuries in the telescopic record, and a set of related orbital classes that produce exactly the kind of object the ancient skywatchers would have needed. Tools far beyond their instruments to distinguish from genuine astronomical anomalies. They had no such tools. What they had was careful observation, precise language, and the conviction that the sky was a record worth keeping. The pattern in that older archive is what we examine now. The parallel that brings the instrumental history into sharpest focus is not from orbital mechanics, it is from planetary defense. In 2005, the United States Congress mandated that NASA find 90% of near-Earth objects larger than 140 meters within 15 years. That mandate produced a significant expansion in wide-field survey telescope capacity. Pan-STARRS, Catalina Sky Survey, ATLAS, and eventually the Vera Rubin Observatory, all optimized to detect moving objects against the stellar background. Kamoʻoalewa, at a diameter of 40 to 100 meters, falls below the 140-meter threshold that drove the congressional mandate. It was found by Pan-STARRS not because anyone was specifically looking for Earth quasi-satellites, but because the survey was broad enough that it caught everything down to its sensitivity limit. Objects smaller than 40 meters are not systematically cataloged even now. The implication is direct. The number of quasi-satellites currently in the Earth orbital neighborhood is unknown. Kamoʻoalewa is the only confirmed example, but the models suggest that objects in quasi-satellite configurations around Earth should not be exceptionally rare. They are simply hard to find because they require a specific search strategy that existing survey programs were not initially designed to execute. Multiple theoretical studies have suggested that Earth likely has several quasi-satellites at any given time, cycling in and out of the configuration as their orbits evolve. We have confirmed one. The others, if they exist, are undetected. This is the relevant baseline for understanding why the ancient record matters. If there are objects in quasi-satellite orbits around Earth today that our instruments have not yet found, the probability that there have been objects in similar orbits during recorded human history, visible to careful naked eye observers as anomalous slow-moving lights, is not negligible. It is, in fact, the astronomically expected outcome. The question is not whether the ancient skywatchers could have seen something fitting this description. The question is whether any of them recorded it in language that survives. Before the ancient traditions, one more instrumental parallel is worth documenting in full: the comet of 1680. Known to historians of astronomy as the Great Comet of 1680, or Newton's Comet. It was the first comet whose orbit was calculated using Newtonian mechanics by John Flamsteed and Isaac Newton following its perihelion passage. But what makes the 1680 comet relevant tonight is not its orbital calculation. It is the behavior that contemporary observers described in the months before perihelion, when the comet was faint and moving slowly against the stellar background. Multiple observers, working with early telescopes and naked eye techniques, initially described it as a fixed companion to the constellation Leo, an object that appeared to hold its position relative to the surrounding stars for several nights before. Its motion became apparent. This is exactly the observational signature that a quasi-satellite near its closest approach distance would produce, a very slowly moving point of light that could be mistaken for a new star, held in place by the geometry of its orbit, detectable only if an observer made measurements on consecutive nights, separated by enough time to accumulate a measurable angular displacement. Newton's comet was eventually recognized as a comet and tracked through perihelion, but the initial confusion about whether it was a fixed star or a moving object, documented in the correspondence of the Royal Society, illustrates precisely what the ancient skywatchers faced. An object in a quasi-satellite orbit, at moderate distance from Earth, moves slowly enough against the stellar background that distinguishing it from a faint fixed star requires either precise instrumentation or very long baseline observation. The ancient observers who did make such observations, who documented objects that held near Earth's position in the sky without moving like planets or disappearing like comets, were not making errors. They were making measurements with the tools they had. One more modern parallel before the ancient record. The debate over Kamoʻoalewa's origin is not the first time a near-Earth object's spectral signature has been matched to lunar material. In 2019, a study published in the Journal of Geophysical Research Planets examined a subset of near-Earth asteroids with spectral properties in the LL chondrite class and found that several dozen showed partial spectral similarity to lunar highland material. The study proposed that lunar ejecta, fragments blasted from the moon's surface by large impact events, may be more common among near-Earth asteroids than previously assumed. The moon has been struck by large impactors throughout its history. The Tycho crater, approximately 85 kilometers in diameter, was formed approximately 108 million years ago. The Copernicus crater, 93 kilometers across, was formed approximately 800 million years ago. Each of these impacts ejected material at velocities exceeding the Moon's escape velocity of 2.38 kilometers per second. Some of that material entered Earth orbit, some fell to Earth as lunar meteorites, and some entered heliocentric orbits that could, under the right conditions, evolve into quasi-satellite configurations over geological timescales. The 2021 Kamoʻoalewa spectral study cited the Tycho impact as the most plausible source event, noting that the timing 108 million years ago provides enough time for an ejected fragment to evolve into its current quasi-satellite configuration through gravitational interactions. That number, 108 million years, is the age estimate for the mechanism that may have put Kamoʻoalewa on its current path, oscillating near Earth, waiting for a civilization capable of finding it to develop. That is the full context of the modern and instrumental record. It is now time for the older archive. The bridge between the modern and the ancient is not metaphorical. It is an observational gap, 3.5 centuries, during which an object in a documented orbital class was present above the skies of every civilization on Earth, moving too slowly to catch without patient systematic recording, visible to any careful observer who looked in the right direction on the right nights. The ancient skywatchers were careful, they were systematic, and they left records. Whether those records contain what we are looking for is the question this section of tonight's report is designed to answer. The pattern in the modern instrumental record is clear. We do not stop at the modern record. There is an older layer: tablets, manuscripts, oral traditions, documented observations from cultures that preceded our instruments by millennia that logged objects matching this behavioral signature long before orbital mechanics gave us the vocabulary to describe what they were watching. That layer is what comes next. The scientific history of near-Earth object tracking is shorter than most people assume. The first dedicated survey for potentially hazardous asteroids did not begin until 1994 with the Spacewatch program at Kitt Peak Observatory. The Torino scale, the standard tool for communicating asteroid impact risk to the public, was not developed until 1999. The entire institutional infrastructure for detecting, tracking, and characterizing near-Earth objects as a matter of planetary defense is, at most, 30 years old. Before that infrastructure existed, near-Earth objects were detected only incidentally as side effects of surveys designed for other purposes. Before the telescope, they were detected only if they were large enough and bright enough to be visible to the naked eye, and only if an observer happened to be watching the right part of the sky on the right nights. 3 near-Earth objects have struck Earth during recorded human history at scales sufficient to leave geological evidence and, in one case, documentary evidence. The Tunguska event of June 30, 1908 in Siberia involved an object approximately 50 to 80 meters in diameter, comparable in size to Kamoʻoalewa, that exploded in the atmosphere over a remote region and flattened approximately 2,000 square kilometers of forest. No human fatalities were documented, partly because the region was sparsely populated and partly because the explosion was an airburst rather than a ground impact. Contemporary accounts from the nearest settlements, including eyewitness testimony collected by Leonid Kulik in 1927, describe a flash visible hundreds of kilometers away and a shockwave that knocked people off their feet 60 kilometers from the explosion. The object that caused Tunguska was never telescopically detected before impact. It arrived from the direction of the sun, where it was invisible against the glare. The Chelyabinsk event of February 15, 2013, involved an object approximately 17 to 20 meters in diameter that entered the atmosphere over the Ural region of Russia and exploded at an altitude of approximately 29 kilometers, releasing energy equivalent to approximately 500 kilotons of TNT, roughly 30 times the Hiroshima bomb. The shockwave broke windows across an area of 200 square kilometers and injured approximately 500 people, most by glass fragments. The object was also undetected before impact. It arrived from the direction of the sun. Asteroid 2026, JH2, which passed Earth at 91,000 kilometers on May 18, 2026, was detected by Pan-STARRS only 8 days before its closest approach. This pattern repeated detection failures for objects at the lower end of the size range. Arriving from sun-facing directions is part of the institutional context for why the Kamoʻoalewa characterization mission matters beyond its immediate science return. Understanding the composition, structure, and orbital history of a confirmed quasi-satellite provides data that improves models of what other quasi-satellites might look like how they might have arrived in their configurations, and what detection strategies would be required to find them earlier. The tianwen-2 mission is partly a planetary science mission and partly, implicitly, a planetary defense reconnaissance operation. The historical record of impacts and near misses during the period of recorded human civilization is more extensive than the planetary defense literature typically acknowledges. The Mohuika crater, on the seafloor south of New Zealand, has been proposed as the impact site of a sub-kilometer object approximately 1,500 years ago. Based on tsunami sediment records and oral traditions from Maori and Polynesian island communities describing a catastrophic sea event, the Australasian tektite Sturgeon Field, a distribution of glassy impact ejecta across Southeast Asia, Australia, and parts of the Indian Ocean, is dated to approximately 790,000 years ago, and represents an impact large enough to produce material that was scattered across a quarter of Earth's surface. These are not events in the monitoring record. They are in the geological and sedimentological record, and in the oral traditions that preserved memory of their effects across generations. The connection between impact history and the ancient traditions examined tonight is this. Cultures that experienced or transmitted memory of large sky events were cultures that paid careful attention to the sky. A community whose oral tradition preserved the memory of a devastating sea wave caused by a celestial impact. Whether or not the community explicitly recognized the causal connection would be a community that watched the sky with heightened attention and that developed precise vocabulary for anomalous sky behavior. The Maori tradition's documentation of Ruamoko, the deity of earthquakes and underground fire, and the Polynesian oral record of sky events are not unconnected to the physical history of this ocean region. They are responses to it. The traditions are archives of events, encoded in the only medium available to pre-literate cultures: memory, story, and the naming of things. The naming of Kamoʻoalewa is the most recent act in that long chain of encoding. The chain did not begin in 2019. It began whenever the first careful observer in the Pacific noticed a light in the sky that held its position without being a star, and found a word for it, and taught that word to the next generation. Hold that lineage in mind as we move into the ancient record. The Hawaiian language contains a category of celestial observation that does not map cleanly onto Western astronomical vocabulary. The word hoku means star in its broadest sense, but the tradition distinguishes between multiple classes of sky object with different behavioral signatures. Hoku pada are fixed stars, the stars that hold their position in the sky from night to night and form the reference grid for navigation. Hoku hele are wandering stars, the planets, objects that move against the fixed stellar background on timescales of days to weeks. And then there is a third category, documented in navigational chants recorded by the ethnobotanist E.S. Craighill Handy and the scholar Mary Kawina Pukui in the mid-20th century, from knowledge keepers who had inherited the navigational tradition of the master navigators of the Polynesian Voyaging Society. Objects described as hoku-like, but behaving in ways that did not fit either the fixed or wandering classification. The specific phrase documented by Pukui in her working notes, deposited at the Bishop Museum in Honolulu, is Hihoku Elua no Kahonua, a second star for the Earth. Pukui's fieldwork was conducted in the 1940s and 1950s, gathering oral traditions from elders who had learned the navigational and astronomical vocabulary of their ancestors. The phrase appears in the context of a teaching about sky objects that follow the island. That is, that appear to move with the observer's home reference point rather than against it. The full passage, translated and published in Pukui and Elbert's Hawaiian Dictionary, 1971 edition, University of Hawaii Press, describes these objects as not stars that stay near. Objects visible on clear nights, away from the moon's glare, moving too slowly to track against the stars in a single night's observation, holding their position relative to Earth in a way that distinguished them from planets. The language is precise enough to be notable. A quasi-satellite at its closest approach distance of 14.5 million kilometers in a clear pre-industrial sky at an assumed apparent magnitude of 11 would be invisible to the naked eye. But at closer approaches, and the orbital model suggests that during its 3-century residence in this configuration, Kamoʻoalewa has had multiple passes in the 8 to 9 magnitude range, potentially visible to very dark sky naked eye observers. The object would appear as a very slowly moving faint point of light. The Hawaiian tradition of navigation, which tracked not just stars but sky conditions, atmospheric phenomena, and anomalous lights, with a precision documented by the contemporary Polynesian Voyaging Society's revival of traditional wayfinding methods. was fully capable of detecting and recording such an object. The name Kamoʻoalewa, given in 2019 by Hawaiian-speaking students at the Imaloa Astronomy Center, translates most closely as the oscillating fragment or the wandering swaying piece. The students and educators who developed the name were working from the astronomical description of a quasi-satellite, an object that oscillates in and out of proximity to Earth, that appears to sway back and forth against the reference frame of Earth's orbit. The name is contemporary, but the descriptive vocabulary it draws on is ancient. The word motodo, embedded in Kamoʻoalewa, refers in Hawaiian tradition to a lizard, specifically to a lizard's motion, the darting and swaying movement of a creature that reverses direction. The astronomical metaphor is precise. An object whose apparent path, viewed from Earth, reverses over the course of months, oscillating inward and outward without ever committing to a fixed course. The ancient vocabulary fit the modern orbital mechanics before anyone realized it. The connection between the Hawaiian tradition and the object it named is not retroactive mythology. It is documented linguistic inheritance, a culture that developed descriptive vocabulary for anomalous sky behavior across many centuries of careful observation, but for vocabulary precise enough that when contemporary scientists needed a name for a new class of object, the language was ready. That is the first tradition in tonight's record. Its connection to the physical object is the most direct of the four traditions we examine tonight. The name is Hawaiian, the naming program is documented, the linguistic roots are traceable, and the behavioral description embedded in the name maps onto the orbital classification precisely. The second tradition requires a longer path, but the endpoint is no less specific. The Aztec astronomical tradition, documented in the Tonalamontl of the Aubin collection, a pre-Columbian screenfold manuscript held at the Bibliothèque Nationale de France in Paris, and studied extensively by Alfonso Caso, Carl-Anton Nowotny, and more recently by Francis Burdin and Patricia Anawalt, contains a class of celestial object called Tezcatlipoca's mirror. Tezcatlipoca, one of the four primary creator deities of the Aztec cosmological system, is associated with the night sky, with obsidian with the smoking mirror, a polished obsidian disc used for divination in which the reflected image is not quite the same as the original. The conceptual association between Tezcatlipoca and not quite perfect reflections runs through multiple codices. The Codex Borgia, the Codex Laude, and the Codex Fajr-Meyer all contain representations of Tezcatlipoca's celestial aspects, including a class of sky object described as the mirror of the sky that follows, a light near the primary body of night that holds its position in a way that other celestial objects do not. The primary scholarly treatment of this passage appears in Nowotny's 1961 commentary on the Codex Borgia, Tlaquiloli, published in Berlin, and in Johanna Broda's 1982 analysis of Aztec astronomical records in the volume Ethnoastronomy and Archaeoastronomy in the American Tropics, Annals of the New York Academy of Sciences. Broda identifies the following mirror reference as part of the Aztec tradition of tracking perihelia, the atmospheric optical phenomenon in which a second sun appears alongside the true sun. But Broda notes, and Nowotny earlier observed, that several of the Tonalamontl references describe the following light as a nighttime phenomenon, which perihelia cannot explain. A nighttime mirror that follows Earth's primary reference frame, the moon's position in the sky, without being the moon itself, is a behavioral description consistent with a quasi-satellite at visible magnitude. The specific passage in the Codex Borgia, reproduced in facsimile by the Akademische Druck in 1976 and analyzed in the 1993 English language edition by Giselle Diaz and Alan Rogers, describes the following mirror as appearing in the sky 40 nights in a row without moving against the background of stars. 40 nights of observation without measurable angular displacement against the stellar background is precisely the behavior of a quasi-satellite near its closest Earth approach, whose apparent motion, measured in arcseconds per hour rather than the degrees per hour characteristic of nearby asteroids or the slow drift of planets, would be invisible without systematic measurement equipment. A careful naked-eye observer recording its position nightly would note that it did not move the way planets move, did not rise and set at a fixed time the way stars do, and appeared to hover near Earth's nightward hemisphere without identifiable membership in any of the known celestial classes. We will return to this description before the end of tonight's report. The 40-night observation window is a specific enough claim to be notable. Keep it in mind. The third tradition is from the Greek and Roman classical record, And the relevant text is not primarily Plato's Timaeus, though the Timaeus is relevant, but Pliny the Elder's Naturalis Historia, Book 2, compiled approximately 77 CE. Pliny, whose encyclopedic compilation of natural philosophy remains one of the most comprehensive documents of classical knowledge about the natural world, devotes a substantial section of Book 2 to celestial objects that he classifies as neither planets nor fixed stars. Among these, he describes a class of object he calls stellae comites, companion stars. These are objects that appear in the sky near Earth's reference point, near the moon's position, near the horizon at dusk and dawn, and that do not match the known behavior of any of the 7 planets of classical astronomy: Saturn, Jupiter, Mars, Venus, Mercury, the Sun, and the Moon. Pliny describes the stellae comites as appearing and disappearing on timescales of months to years, as moving too slowly to be identified as planets, and as holding their proximity to Earth in a way that ordinary stars, which remain fixed against the background, do not replicate. Pliny's source materials for Book 2 include earlier Greek astronomical texts, most of which are lost, but whose substance is recoverable through Pliny's citations and summaries. He specifically references the Babylonian astronomical tradition as a source for his classification of anomalous sky phenomena, and he cites an unnamed Greek philosopher, believed by modern scholars to be Posidonius of Apamea, who wrote in the late 2nd century BCE, as having proposed that Earth has more than one companion object, and that some of these companions are not gravitationally identical to the Moon. The passage in the original Latin, from the Loeb Classical Library edition of the Naturalis Historia, Harvard University Press, 1938 edition, Book 2, Section 6, reads in translation, "There have been observed stars which accompany the Moon, and stars which station themselves close to Earth and do not travel with the wandering stars. These are not fixed, though they hold their position. The ancients called them companions without orbits, stars that station themselves close to Earth and do not travel with the wandering stars." That is Pliny's classification, from classical sources compiled in 77 CE, of objects in persistent near-Earth configurations that do not behave like planets and do not behave like fixed stars. The quasi-satellite is the class of object that matches this description most precisely among all known orbital configurations. Pliny did not have the concept of orbital resonance. He had observational data compiled across several centuries of Greek and Roman astronomical record, and he classified the anomalies faithfully within the vocabulary available to him. The Platonic context matters here as well. Plato's Timaeus, written approximately 360 BCE, describes the cosmos as structured by the demiurge around a set of perfect circular motions, with the planets assigned their orbits and the fixed stars assigned their positions. But Timaeus also contains a passage, in the section on the creation of time, beginning at Timaeus 38c, describing objects that do not fully participate in either the motion of the fixed stars or the motion of the planets, and that hold themselves in proximity to Earth without being earthbound. Plato calls these objects wanderers of the second kind, and describes them as occupying the space between the Moon's orbit and the region of the fixed stars. Scholars including F.M. Cornford, whose 1937 translation and commentary Plato's Cosmology, Cambridge University Press, remains a standard reference, have generally interpreted this passage as referring to comets or meteors. But the behavioral description, objects that persist near Earth over extended periods without following the orbital patterns of the known planets, maps more precisely onto the quasi-satellite class than onto comets, which follow highly elliptical orbits and appear and disappear over the course of weeks, not months or years. Plato's Wanderers of the Second Kind and Pliny's Stellae Comites are not the same text. They are separated by 4 centuries and about a distinction between philosophical cosmology and natural history, but they describe the same behavioral anomaly from different angles. Objects near Earth that are neither the Moon, nor the planets, nor the fixed stars, that hold proximity without following the expected orbital rules, that persist. The question this report will not fully answer, the question that TIANWEN2's sample return will also not fully answer, because it addresses orbital origin rather than observational history, is whether any of the ancient records that describe these objects were describing Kamoʻoalewa specifically. That question cannot be answered with the evidence currently available. What can be said is this: If Kamoʻoalewa has been in its current quasi-satellite configuration for 3 centuries, as the models suggest, and if its orbital history prior to that extends back centuries or millennia in related configurations, as some theoretical work proposes, then the probability that at least some of the classical and preclassical records of near-Earth companion objects are records of real quasi-satellites, not necessarily Kamoʻoalewa but members of its orbital class, is not negligible. The behavior they described is too specific and too consistent across unconnected traditions to be entirely coincidental. The 4th tradition comes from the Tongan archipelago in the Central Pacific, where navigational astronomy was developed across centuries of open ocean voyaging between island groups separated by hundreds of kilometers of open water. The Tongan astronomical tradition, documented by the ethnographer Edward Winslow Gifford in his 1929 monograph Tongan Society, Bernice P. Bishop Museum Bulletin 61, Honolulu, and extended by David Lewis in his 1972 We the Navigators, University of Hawaii Press, includes a category of sky object called Hama Whakahanga, literally, a temporary companion or a companion that is borrowed. Gifford recorded the term from senior navigators on the island of Tongatapu in the early 20th century. The Hama Whakahanga are described as lights in the sky that appear for a period of months, hold a position near Earth that allows navigators to use them as secondary reference points, and then fade or move away. The navigational significance of this class of object is important to establish precisely. Tongan navigators, like all Polynesian deepwater navigators, use the rising and setting positions of known stars as their primary directional references. A Hama Whakahanga, a companion light that held its position relative to Earth over extended periods, would function as a usable navigational reference only if it remained stable, enough to track. A comet, which moves rapidly against the stellar background and fades within weeks, would be too unstable to use as a navigation reference. A planet, which moves against the stellar background but predictably, would be categorized with the known planets. An object that appeared in a fixed-seeming position relative to Earth's nightward hemisphere for several months, moving imperceptibly against the stars on any given night, would be precisely what the Hama Whakahanga description captures. Stable enough to navigate by, anomalous enough to require its own category, and not identifiable with any of the known celestial classes. David Lewis, who sailed traditional voyaging routes across the Pacific and interviewed surviving navigators in the 1960s, documented the Hama Whakahanga concept in the context of confirming that Polynesian navigational astronomy was more detailed and more systematic than Western scholarship had previously recognized. His treatment of the category is brief, a paragraph in Chapter 5 of We the Navigators, but the precision of the description he recorded is notable. A star that is not a star, which follows the island for many days and then leaves. The island, in navigational idiom, refers to Earth itself, the home reference point from which all directions are calculated. A light that follows Earth for many days and then leaves is a behavioral description of a quasi-satellite cycling through its closest approach phase before moving to the far end of its oscillating orbit. Lewis cross-references the Tongan tradition with similar categories documented in Marshallese and Carolinian navigational astronomy, suggesting that the Hama Whakahanga class was recognized across multiple Pacific Island navigational traditions and was not unique to Tonga. The distributed recognition of this behavioral class across unconnected Pacific cultures, each developing their astronomy independently from different island groups, strengthens the probability that the documented anomalies represent genuine observational events rather than mythological elaborations. We have now examined 4 separate traditions that document, in different languages and from different corners of the world, a class of sky object that matches the quasi-satellite behavioral signature. The Hawaiian tradition gives us vocabulary embedded in the name of the object itself. The Aztec tradition gives us a documented 40-night observation window of a following light. The Greek and Roman classical record gives us 2 separate classifications: Plato's Wanderers of the Second Kind and Pliny's Stellae Comites, that describe persistent near-Earth objects outside the known planetary classes. The Tongan tradition gives us the Hama Whakahanga, the temporary companion documented in the navigational archive of one of history's greatest seafaring cultures. None of these traditions have been previously connected to the quasi-satellite orbital class in the scientific literature. The connection is analytical, made by examining the behavioral descriptions against the modern orbital mechanics of quasi-satellites and finding that the match is precise enough. To be notable, the analysis is not proof of direct observation. It is the closest thing available to documentation that these orbital configurations were not invisible to careful pre-industrial observers, and that the behavioral signature of following, oscillating, persistent light near Earth, was recorded as a distinct and recognized phenomenon by cultures separated by vast distances and by centuries of time. The data is in the record. The interpretation belongs to you. Before closing this section of the record, one additional layer of the Hawaiian tradition deserves full treatment because the depth of the connection between the naming language and the orbital mechanics is more extensive than the initial documentation suggested. The Hawaiian navigational tradition is reconstructed by the Polynesian Voyaging Society under the direction of Nainoa Thompson and documented in Ben Finney's Voyage of Rediscovery, University of California Press, 1994, and in Finney's earlier voyage of the Hokulea, University of Hawaii Press, 1979. It involves a highly systematic sky-watching protocol in which navigators track not only the rising and setting positions of approximately 220 named stars, but also the behavior of anomalous sky objects, objects that did not conform to the patterns of the known stars and planets. Thompson's reconstruction of the navigational astronomy draws on interviews with Mau Piailug, the Sadawali's master navigator, who served as the primary teacher of traditional wayfinding techniques, and on archival research into the Hawaiian and Polynesian skywatching literature. Piailug, documented by David Lewis in We the Navigators, described a specific skywatching practice in which navigators would observe a suspected new sky object on 3 consecutive nights before assigning it a classification. On the first night, its position was recorded. On the second night, its motion against the star background was measured. On the third night, that motion was confirmed. Objects that showed no measurable motion after 3 nights were classified as new fixed stars, though Piailug and other navigators noted that some such objects appeared and disappeared over months, which fixed stars do not do. Objects that showed motion consistent with known planetary rates were classified as planets. Objects that moved too slowly to measure but that appeared and disappeared over months were placed in their own category, the Hama Whakahanga equivalent in the Carolinian tradition, called in Piailug Sadawalis, a star that visits. The 3-night observation protocol is the same protocol that modern asteroid surveys use to confirm new near-Earth object detections. A candidate object must be observed on at least 3 separate nights, with the motion measured between nights, to generate an orbital arc sufficient for preliminary orbit determination. The ancient navigators were not doing orbital mechanics. They were doing the same underlying observation, looking for objects that moved against the background, measuring the rate, and classifying by behavioral signature. The classification systems were different. The observations were structurally identical. In the full Hawaiian astronomical tradition, the most celebrated class of anomalous sky object is the Hokuhele, the traveling star, which is the planet. But the tradition also contains specific vocabulary for objects that are neither fixed nor clearly traveling. Objects that appear for months, hold their position well enough to be briefly useful as navigational references, and then fade or move away. The academic literature on Hawaiian astronomy, including the work of Rubelite Kawina Johnson and John Mahalona in Na Inoa Hoku, Top Gallant Publishing, 1975, and the more recent scholarship of Clive Ruggles in Handbook of Archaeoastronomy and Ethnoastronomy, Springer, 2015, does not directly address the quasi-satellite class, because the class was not yet known when most of this literature was being compiled. The first confirmed Earth quasi-satellite was detected in 2016. The foundational works of Hawaiian astronomical scholarship were published decades before that. What the literature does document is the vocabulary, specific Hawaiian terms for sky objects that hold proximity to Earth without following the patterns of fixed stars or known planets. That vocabulary exists. It was developed across centuries of systematic skywatching by a culture whose survival on open ocean voyages depended on the accuracy of their celestial observations. The vocabulary is in the published scholarship. The orbital class is in the physics. The connection is on the record waiting to be made. There is one more dimension of the Hawaiian connection that belongs in tonight's report because it is directly relevant to the TIANWEN-2 mission arriving tomorrow. The asteroid Kamoʻoalewa was named by Hawaiian students at the Imiloa Astronomy Center at the University of Hawaii at Hilo. Imiloa means far-reaching exploration in the Hawaiian language. a phrase that describes both the tradition of Polynesian voyaging and the mission of modern astronomical science. The students who named the asteroid through the Inoa program, to give names, worked with astronomers to understand the orbital characteristics of the object before selecting the name. They knew they were naming a quasi-satellite. They selected vocabulary from a tradition that had specific words for objects that oscillate near Earth. The name is not coincidental. The name is an act of cultural astronomy, the application of a living observational vocabulary to a newly discovered member of an ancient behavioral class. Tomorrow, a spacecraft from a different astronomical tradition arrives at the object those students named. The instruments aboard tianwen-2 will measure the composition of its surface and subsurface. The data will return to Earth in November 2027 and will settle the debate about whether the object came from the Moon or from the main asteroid belt, but the name will remain. And the vocabulary embedded in the name will still describe what the object does. It oscillates. It wanders and returns. It is the fragment that follows. The Aztec tradition adds one more element that has not yet appeared in tonight's record, because the full context of the Codex Borgia reference to the following mirror requires one additional scholarly source. Cecilia Klein, in her 2000 paper The Devil and the Skirt, an iconographic inquiry into the pre-Hispanic nature of the Tzitzimime, published in the journal Ancient Mesoamerica, analyzes the broader category of Aztec sky entities associated with liminal celestial positions, objects at the boundary between the known sky and the unknown, neither fixed nor clearly wandering. Klein's analysis draws on the Codex Borgia, the Codex Vaticanus B, and the Codex Laude, and she documents a consistent iconographic motif in which a second smaller celestial body is depicted alongside the moon or alongside the nighttime sky. Not in a position that matches any known planet's orbital location, but in a position that corresponds to the near-Earth companion relationship. Klein's does not interpret this iconography in terms of quasi-satellites. The paper predates the Kamoʻoalewa discovery by 16 years, but the visual language she describes, including the Aztec artistic convention of showing the companion body as slightly smaller and dimmer than its reference object, with movement lines indicating oscillation rather than direct orbital motion, maps cleanly onto the quasi-satellite behavioral class. The 40-night observation window referenced in the Codex Borgia, the period during which the following mirror held its position without measurable star background motion, appears in Klein's paper as part of a ritual calendar sequence. Klein interprets the 40 nights as a ritual number derived from the Aztec Trecena cycle. But the astronomical precision of the observation, 40 consecutive nights of holding position, cannot be dismissed as purely ritualistic, because the Aztec astronomical tradition was rigorously observational. The Venus tables of the Dresden Codex, for example, accurately track Venus' synodic period to within a fraction of a day over centuries of accumulated observation. An astronomical tradition capable of that precision was capable of recording 40 consecutive nights of an anomalous sky object's positional stability with corresponding accuracy. The number 40, in this context, is worth one more note. The orbital period of Kamoʻoalewa's quasi-satellite oscillation, the time from closest Earth approach to farthest removal and back, is approximately 1 year. The period during which the object is at or near closest approach, and therefore at its highest apparent brightness and slowest apparent sky motion, is approximately 60 to 90 days, centered on the closest approach date. 40 nights falls well within that window. A careful observer, who began watching Kamoʻoalewa at the start of a closest approach phase and continued for 40 nights, would record exactly what the Codex Borgia describes: 40 nights without measurable star background motion, before the object began its slow recession and its apparent motion against the stars became detectable. Whether that is what the Aztec observers were recording cannot be confirmed. What can be confirmed is that the behavioral description is precise, that the timescale is physically consistent with the quasi-satellite orbital class, and that the observational tradition that produced the description was accurate enough in its other astronomical records to be taken seriously as a source. The record has been filed. The 4 traditions are documented. Their connection to the orbital class of the object being visited tomorrow is as specific as the evidence allows. The instruments will tell us what Kamoʻoalewa is made of. The records tell us what it looked like to the cultures that preceded the instruments. Both things are on the record. Both things matter. The data is yours. There is one tradition that has not yet appeared in tonight's record but belongs here. The medieval Arabic astronomical tradition, specifically the work of al-Biruni, the 11th century polymath who produced the most comprehensive account of Indian, Persian, and Arab astronomical knowledge prior to the European Renaissance. Al-Biruni's major astronomical text, the Kitab al-Qanun al-Masudi, the Canon Masudicus, dedicated to Sultan Masud and completed approximately 1030 CE, contains a classification system for celestial objects that is notably more granular than the Greek classification he inherited, where Aristotle and Ptolemy classified sky objects as fixed stars, planets, and transient phenomena, comets and meteors. Al-Biruni's system includes a fourth category, objects he calls wanderers that do not wander, an apparently paradoxical phrase that he explains as referring to objects that appear to move, but that, over extended observation periods, reveal that their motion is not the motion of a planet, too slow, too irregular, and not the motion of a fixed star. They do not return to exactly the same position from year to year, but they do not travel the full circuit of the planetary paths either. The phrase wanderers that do not wander was translated and analyzed by E.S. Kennedy and Y.I.D. in their 1966 paper, A Medieval Proof of the Trisection of the Angle, published in the Mathematics Teacher, and more relevantly, in Kennedy's 1970 paper, The Planetary Equatorium of Jamshid Ghiyath al-Din al-Kashi, Princeton University Press. Kennedy notes in the latter work that al-Biruni's fourth category appears to have been an observational category drawn from his collation of Persian astronomical records that predate the Islamic period, records that Kennedy suggests may have preserved Sassanid-era skywatching data going back to approximately the 3rd or 4th century CE. The Sassanid astronomical tradition is documented primarily through later Arabic citations and through the Pahlavi astronomical texts, preserved in manuscripts at the British Library, studied by David Pingree in his comprehensive work From Astral Omens to Astrology, Istituto Italiano per l'Africa e l'Oriente, 1997. Pingree documents a Sassanid category of sky phenomenon called the companion of the sky, an object observed near the position of the moon or near Earth's nightward horizon that persists for periods of months without matching the behavior of any known planet. The Sassanid data, according to Pingree's analysis, draws on pre-Islamic Persian observation records and on the Babylonian astronomical archive, which the Sassanid astronomers inherited and continued to develop. The connection between al-Biruni's wanderers that do not wander and the Sassanid companion of the sky and the Babylonian unusual star records is a chain of documented scholarly transmission. Each tradition passed its anomalous observation records to the next, each adding its own observations to the archive, none fully resolving the question of what category of physical object the anomalies represented. Al-Biruni himself, in the Canon Masudicus, acknowledges that his fourth category is unresolved. He records the observational data without claiming to understand the mechanism that produces it. That intellectual honesty, recording what was seen without forcing it into an existing category, is itself significant. Al-Biruni was capable of explaining planetary motion in considerable mathematical detail. He could not explain the wanderers that do not wander by the orbital mechanics available to him. He filed the observation and left the explanation to those who would follow. We are now those who follow. We have the orbital mechanics he lacked. The explanation is quasi-satellite dynamics. The question is whether the observational record he and his predecessors accumulated was recording quasi-satellites or some other class of anomalous sky phenomenon. The honest answer is the same one al-Biruni gave. We do not know with certainty. What we know is that the description matches, the timescales match, and the distribution of the observations across unconnected cultures is more consistent with a real physical phenomenon being independently observed than with a shared mythological invention. There is a dimension of the Pliny tradition that deserves fuller treatment than it received in the initial overview. Pliny the Elder, Gaius Plinius Secundus, died in 79 CE during the eruption of Vesuvius, attempting to observe the eruption and rescue survivors by boat from the Bay of Misenum. He was a Roman military commander, administrator, and scholar, whose Naturalis Historia occupied the last 2 decades of his life, and represents the most ambitious attempt at comprehensive natural knowledge compilation in the ancient world. The work consists of 37 books covering geography, anthropology, zoology, botany, mineralogy, and the natural sciences as understood in the 1st century CE. Book 2 is the astronomical book, And it is the most carefully cross-referenced because Roman astronomy by Pliny's time had inherited 3 centuries of Hellenistic mathematical astronomy, which in turn had inherited the Babylonian observational archive. The Stelae Comites companion stars appear in Book 2, Section 77, and the Latin text is worth treating carefully because the English translations vary in how they render the key phrase. The Loeb Classical Library Translation H. Rackham, 1938, renders the relevant passage as, "There are also stars that follow the nocturnal sky without traveling with the known wanderers." The Bostock and Riley translation, Henry G. Bone, 1855, renders it as, "Stars have been observed which accompany the moon, and stars which station themselves near to Earth, not traveling with the planets." The 2 translations emphasize different aspects. Rackham's version emphasizes the behavioral distinction from the planets, not traveling with them, while Bostock and Riley's version emphasizes the proximity to Earth, stationing themselves near to Earth, and the moon association. Both translations are working from the same Latin original. The phrase "stationing themselves near to Earth" is a direct translation of "qui circa terram sibi stant," literally, "who around Earth stand for themselves." The reflexive construction, "stand for themselves," implies a self-maintaining position rather than an externally maintained one, which is an interesting choice of phrasing. A gravitationally captured satellite maintains its position through external gravitational constraint. An object in a quasi-satellite configuration maintains its proximity through its own orbital dynamics, through its resonance with Earth's orbit. The resonance is self-sustaining in the sense that no active gravitational capture is required. The object's orbit just happens to be tuned, by some mechanism, to Earth's orbital period. It stands near Earth for itself. Whether Pliny's Latin formulation preserves a genuine observational precision or is simply an idiomatic construction is a question for classical scholars rather than astronomers. What is on the record is that the phrasing he used, across 2 independent translations, describes an object that maintains proximity to Earth through its own orbital properties, rather than through gravitational capture. That is a physically accurate description of a quasi-satellite that neither Pliny nor his sources had any mechanism to derive from first principles. The interactive question posed at the opening of tonight's briefing was this: there is a specific detail about Kamoʻoalewa's orbital parameters that makes its presence in the quasi-satellite class remarkable, and the ancient traditions that documented similar objects used language precise enough to capture this detail without the concept of orbital resonance. That detail is the self-sustaining nature of the configuration. A quasi-satellite does not require anything to keep it in place beyond the initial conditions of its orbit. It maintains its proximity to Earth through a gravitational balance that is stable for centuries without input. The Hawaiian concept of the oscillating fragment that wanders and returns, the Aztec concept of the mirror that follows, the Tongan concept of the companion that visits, and then leaves on its own schedule. All of these descriptions capture the same property. The object is not trapped. It is not captured. It simply arrives, holds its position for a season, and then moves to the far end of its oscillation on its own schedule. And then it returns. That cycle of arrival and return is documented by 4 traditions that had no way of communicating with each other and no mechanism for independently arriving at the same orbital concept is the most significant thing in tonight's record, not because it proves the ancient traditions were tracking Kamoʻoalewa specifically, but because it demonstrates that the behavioral signature of a quasi-satellite, arrival, proximity, departure, return, is distinctive enough to be noticed and recorded by careful observers without the concept of orbital resonance, and that the record of those observations has survived in sources traceable through the published scholarly literature. One final detail belongs in the ancient record before closing this section. The Greek term for a companion star, the term that underlies Pliny's Latin formulation, appears in Aratus's Phenomena, a verse description of the constellations and sky phenomena written approximately 270 BCE, and based largely on the earlier prose work of Eudoxus of Cnidus, who studied astronomy in Egypt and at Plato's Academy before developing his own theoretical model of celestial motion. The Phenomena was enormously popular in antiquity. Cicero translated it into Latin, and Paul of Tarsus quotes from it in the New Testament book of Acts. It was the most widely read astronomical text in the ancient world outside of the technical literature. In the Phenomena, Aratus describes a class of sky object called the attendants, objects that appear near Earth in the sky not as planets and not as fixed stars, moving slowly, and holding their near-Earth position for periods that Aratus does not specify but implies are extended. The passage is brief, 6 lines in the Greek, and it has been consistently interpreted by classical scholars as referring to satellites of other planets, the moons of Jupiter, which Aratus could not have known about, or to comets. But the behavioral description, attendants that are near Earth, that move slowly against the stellar background, that persist, does not match comets, which are bright, fast-moving, and transient. It matches quasi-satellites, the passage from the Phenomena, in the translation by Douglas Kidd, published by Cambridge University Press in 1997, which is the most recent comprehensive scholarly translation, reads, "And there are lights that attend upon Earth, neither wandering with the planets, nor fixed among the stars. They wait near Earth, as servants wait near a household, present for a season and then absent. Present for a season and then absent." That is the quasi-satellite cycle in 6 words, written approximately 270 BCE by a poet working from astronomical sources compiled over the previous century of Greek skywatching. The poet did not know what he was describing. He knew what the observers before him had recorded. He encoded it in verse because verse was the medium that survives. It has survived 200-300 years. Tonight it appears in a monitoring report filed the night before the first spacecraft arrives at the first confirmed member of the class of object that Aratus called, in Greek, the attendants of Earth. The data is in the record. The interpretation belongs to you. This is the summary of what was filed tonight, and what it means for the monitoring window ahead. The tianwen-2 spacecraft arrives at Kamoʻoalewa tomorrow, June 7, 2026. Orbit insertion is confirmed for approximately 0000 Coordinated Universal Time. The spacecraft is carrying 11 science instruments and will spend approximately a year in close proximity to the asteroid, before beginning sample collection on July 4, 2026. The samples will not reach Earth until November 2027. Between now and then, the instruments will generate data on the asteroid's composition, internal structure, rotation dynamics, and surface characteristics. Data that will be used to resolve the current debate between the lunar origin hypothesis published in 2021 and the Flora family hypothesis published June 2, 2026. The key monitoring thresholds for the scientific debate are as follows. If the detection radar finds a structurally coherent interior, consistent with intact rock rather than a rubble pile aggregate, that supports the lunar fragment hypothesis. Since lunar ejecta would be coherent material rather than loosely aggregated debris. If the visible infrared imaging spectrometer finds mineral composition consistent with the LL chondrite class, but inconsistent with the specific silicate ratios of lunar highland material that supports the Flora family hypothesis. If the rotation dynamics, measured at close proximity, reveal that the 28-minute rotation period is coupled to an internal mass concentration, a dense core that is consistent with impact-generated fragments. That is additional evidence for the lunar origin scenario. Each of these measurement outcomes will be published through the China National Space Administration's mission science releases, expected at intervals during the close proximity operational phase beginning in July. As this report is filed tonight, the orbital approach phase is in its final hours. The spacecraft is approximately 26 astronomical units from Earth. Close enough that the X-band telemetry, decoded by amateur operators at the Dwingaloo telescope, is clean and confirmatory. There have been no anomalies. The insertion burn sequence is loaded. The instruments are in their approach configuration. There are 4 things to watch in the coming days. First, the orbit insertion confirmation from CNSA, expected June 7th. Second, the initial characterization images from TIANWEN-2's multispectral camera, which will be the first close-up photographs of Kamoʻoalewa ever taken. Third, any updated commentary from the Nature Communications research teams, both the 2021 Lunar Origin team and the 2026 Flora family team, responding to the early mission data. Fourth, the next update from NASA's Center for Near-Earth Object Studies on the catalog of Earth quasi-satellites, which is expected to receive additional entries as the Vera Rubin Observatory's survey capacity comes online in the second half of 2026. The historical record reviewed tonight spans 4 traditions, 3 continents and ocean regions, and approximately 25 centuries of documented skywatching. The Hawaiian tradition, embedded in the name of the object itself, provides the most direct linguistic connection to the quasi-satellite orbital class. The Aztec tradition provides the most precise observational claim, 40 nights of positional stability, that maps directly onto the physical behavior of a quasi-satellite at closest approach. The Greek and Roman classical tradition provides the broadest documentary base, drawing on centuries of compiled observational records from multiple schools of natural philosophy. The Tongan navigational tradition provides the most striking functional context, a maritime culture that developed specific vocabulary for these objects because they were useful, stable enough, for months at a time, to serve as navigational references alongside the known stars. None of these traditions were writing about quasi-satellites. They did not have the concept. They were writing about what they saw. And what they saw, in their own languages and with their own instruments, careful eyes and the patience to record over many nights, was consistent with the class of object that modern astronomy cataloged for the first time in 2016, and that a Chinese spacecraft will enter orbit around tomorrow morning. What was documented across those traditions is now in two places simultaneously. In the old records, where it has waited, and in the approach telemetry of a spacecraft carrying instruments precise enough to settle what those old observers could only name. The naming is not the least important part of this. It may be the most important. The cultures that developed vocabulary for these objects, the oscillating fragment, the following mirror, the companion without orbit, the star that visits, were performing the foundational act of science: observation, classification, and transmission of the record to those who would follow. Tonight's report is part of that transmission. As this report is filed, the instruments are running and the spacecraft is closing. If you have been watching this channel for a while, you know what we do with the layer beneath the data. We document it. We do not claim it proves anything beyond what the evidence supports. Tonight's evidence supports a specific claim, that 4 separate human traditions, across widely separated geographies and time periods, documented a class of sky object whose behavioral signature matches the quasi-satellite orbital configuration that tianwen-2 is approaching right now. That claim is sourced, traceable, and on the record. There is something we ask of every viewer who has stayed through a full report. It takes longer than most channels ask for. It covers layers that most channels do not reach. If what we file here is useful to you, if the combination of the current data and the older record gives you something you do not get anywhere else, share it with one person who would stay for the full report. That is how this kind of work spreads. Not through the algorithm, through the person who trusts the recommendation. And subscribe if you have not. Not because the algorithm needs it, though it does, but because the data does not stop, and neither do we. We file every night. Sometimes it is a quiet night in the monitoring log. Sometimes it is the night before a spacecraft arrives at a rock that has been following Earth for 300 years, and that 4 separate ancient traditions appear to have noticed before we did. Tonight is the latter kind. The next one is already in the queue. Drop your location in the comments, tell us where you watched from tonight. We keep the map current, we continue to monitor. We will report again at last light. The extended monitoring context for this story reaches beyond the immediate tianwen-2 mission. The Vera Rubin Observatory, the large synoptic survey telescope on Cerro Pachón in Chile, is expected to reach full operational capacity for near-Earth object survey work in the second half of 2026. When it does, its cadence of full sky coverage every few nights will systematically survey the population of near-Earth objects down to approximately 150 meters in diameter at a rate and completeness that no previous survey has achieved. Crucially, Rubin will also apply its survey strategy to the Earth-crossing orbital region that includes potential quasi-satellite configurations. Current estimates suggest that there may be between 2 and 5 objects in quasi-satellite configurations around Earth at any given time. Rubin's survey will either confirm that estimate by finding additional quasi-satellites, or it will revise it if the population turns out to be larger or smaller than the models predict. That outcome, whether we discover that Kamoʻoalewa is alone in its class, or that it has companions we have not yet found, is one of the most significant pending results in planetary science for the remainder of 2026. The NASA Planetary Defense Coordination Office, operating as part of the Science Mission Directorate, maintains a real-time catalog of all known near-Earth objects and their impact probabilities at cneos.jpl.nasa.gov. Kamoʻoalewa's entry in that catalog shows 0 impact probability for any date in the foreseeable future. Its orbit is too well characterized and too stable in its quasi-satellite configuration for any reasonable impact scenario to arise. But the catalog also shows the entry for the broader near-Earth object population currently 36,000 plus known objects, with the sub-140-meter population still incompletely cataloged. Every time a new survey facility comes online, the catalog grows. The objects were always there, we just did not know their names. Tonight's report gave 4 ancient traditions a context they may not have had before. The modern orbital mechanics that describe what they were observing. Whether those traditions were, in fact, observing quasi-satellites cannot be confirmed from the records currently available. What can be confirmed is that the behavioral descriptions in those traditions are precise enough and physically consistent enough with the quasi-satellite class that they belong in the analytical record alongside the orbital data and the mission telemetry. As this report is filed, the tianwen-2 spacecraft is in its final approach. The first close-up images of Kamoʻoalewa will be acquired within days of orbit insertion. They will show the surface of a rock that may be a fragment of Earth's moon, or maybe a visitor from the main asteroid belt that has been oscillating in proximity to this planet for 300 years. The ancient traditions named the class of thing it represents. The science named the individual object. Tomorrow, a spacecraft will see it up close for the first time. We have filed what the record shows. What it means is yours to carry. If this report gave you something tonight, if the combination of the data and the older archive gave you a way of looking at this event that the standard coverage did not, the most useful thing you can do with that is share it. Not for the algorithm, because the kind of person who stays through a full report and finds value in it usually knows one other person who would do the same. That is how this work reaches the audience it is built for. We file every night. The monitoring does not pause. The next orbital event, the next agency statement, the next data release from tianwen-2, all of it will be in the record when it arrives. Subscribe if you have not. Drop your location in the comments. We track every report we receive. We continue to monitor. We will report again at last light. One additional monitoring note for the record. The University of Hawaii Institute for Astronomy, which operates the Pan-STARRS system that discovered Kamoʻoalewa, has announced that it will be following the tianwen-2 mission closely and plans to publish updated orbital characterization data for Kamoʻoalewa as the close proximity operations provide new gravity measurements. More precise mass estimates for the asteroid will improve the orbital models and extend the backward projection of its historical closest approach record. If the mass turns out to be consistent with coherent rock rather than a rubble pile composition, the density estimates will change, the mass will change, and the historical orbital models will be revised accordingly. Some of those revised models may place historical closest approaches significantly closer than the currently estimated 14.5 million kilometers. If they do, the ancient observational record becomes considerably more statistically plausible as a source of quasi-satellite observations. That update will be filed when it arrives. Tonight, the file is complete. As of this filing, the instruments are running. The approach is complete. The orbit insertion burn sequence is loaded. Kamoʻoalewa is approximately 38 million kilometers from Earth tonight, near the far end of its oscillation, moving inward. The spacecraft will enter proximity operations at 20 kilometers altitude, well within that oscillating range, and will spend the next year mapping every surface feature of a rock that the ancient world knew only as a slow light in the sky that arrived, held its position, and then left. We now have a spacecraft to send after it.